The goal of this segment is to learn how to use so-called EZ notation in order to specify the stereochemistry of alkenes. In the last segment, we talked about specifying the stereochemistry of alkenes using the cis and trans designations. In the cis and trans designations, we followed the longest carbon chain and evaluated whether, relative to the carbon-carbon double bond, both bonds going with the longest carbon chain went on the same face of the molecule to make the molecule cis, or whether they went opposite, making the molecule described as trans. EZ notation is an alternative way of going about specifying stereochemistry, and EZ notation is typically the notation that is used in more complex cases. In other words, if we're dealing with a molecule that has multiple alkene groups, or a molecule that has additional functional groups in addition to just alkenes and alkyl branches, then we'll typically use EZ notation to indicate the stereochemistry. So we're going to go through the guidelines for assigning EZ stereochemistry to a molecule, and then we'll do some example problems of that. So first off, when we're talking about EZ notation, we can think of this as being analogous to RS notation in that the different stereoisomers of an alkene are going to come in two different forms, the E form or the Z form, much like chiral centers can come in the R and S forms. So when we're talking about the E and Z forms, what we're referring to is if we look at the carbon-carbon double bond, so we'll draw our carbon-carbon double bond in here, and we look at the four groups that are bonded there. Specifically, we're going to focus on the two groups over here on the right and compare those. We're going to focus on the two groups on the left and compare those to come up with this molecule as having the E or the Z configuration. So the way I like to approach this is to remind myself that I'm going to focus on which of the two groups directly bonded to this carbon on the right is higher ranking, and then separately I'm going to ask which of the two groups on the left is higher ranking. I'm going to draw just a squiggly line through the double bond to kind of mentally separate those out. I'm going to look at that carbon atom on the right that I've put the red dot in and ask which of those two groups, bromine or a methyl group, is higher ranking. And the higher ranking is determined using the same guidelines that we used for the R and S notation. So remember, those guidelines were based on higher atomic number. So use the same guidelines that you used for assigning R and S to determine the relative rank of those. And remember, that's an atomic number based assignment. So we're looking for the atom that's directly bonded here that has a higher atomic number. And if there's a tie, then we go one more spot down the chain looking at what's directly bonded there. So we're going to use the same guidelines for assignment here as we did for R and S. We're comparing a bromine atom to a carbon atom because those are what are directly bonded to that alkene carbon. Bromine has a higher atomic number, so therefore it is going to take priority. So I'm going to put a red circle around that to indicate that that is the higher priority group bonded to this carbon. Then we take a look at the left-hand carbon there of our carbon-carbon double bond. That is the carbon on the left that's got the red dot on it. And we ask ourselves which of those two groups is higher ranking, a hydrogen or the methyl group there on the lower left. The methyl group, of course, has a carbon directly bonded to the alkene. Carbon has a higher atomic number than hydrogen, so therefore the CH3 group takes priority. Now what you will see is that the two higher ranking groups are on the same face of the molecule. When the two higher ranking groups are on the same face of the molecule, we describe the molecule as being the Z diastereomer. So here, the two higher ranking groups, the bromine and the methyl group, are on the same face, meaning they're both pointed downward relative to the carbon atom that they're bonded to, and therefore we describe the molecule as having the Z configuration. So Z refers to the two higher ranking groups, that is the higher ranking group on the right and the higher ranking group on the left, are on the same face of the molecule. So two higher ranking groups on the same face. And remember that the way that we evaluate the face of the molecules, we ask ourselves whether the bond to that group goes upward or downward relative to the carbon atom that's bonded to. So here, both the bond here to the higher ranking group and the bond here to the higher ranking group both go downward, and therefore we describe the molecule as being Z. You may be wondering why in the world we refer to this as Z other than just to confuse you. So the Z term stands for zusammen, which in German, where this terminology was derived from, refers to together. And so what we're saying is that the bromine and the methyl group are together on the same face of the molecule. So we could draw the diastereomer of this molecule. That is where we've gone from the Z form to the E form meaning that the two higher ranking groups are on opposite faces. So what I'm going to do here then is change the position of the bromine so that rather than being bonded on the lower right, it's bonded on the upper right. So we just changed the position of the CH3 and the bromine there on the right hand side. We're going to leave the left hand side exactly the same, so that now when we look at the higher ranking group that's bonded to the right hand carbon, so the right hand carbon I put a red dot on, higher ranking group bonded there is the bromine. We look at the carbon on the left, right here, and the higher ranking group there is our carbon atom. Now what we see is that those two groups are on opposite faces of the molecule. And so we're going to use the term E. E stands for entgegen. Entgegen means opposite in German. So E refers to the two higher ranking groups are on opposite faces of the molecule. Okay, and we can tell that they're on opposite faces because if we look at the carbon atom here on the right and we ask what direction we have to go to get to that higher ranked bromine, we have to go upward. If we look at the other carbon and ask how to get to the methyl group, we have to go downward. So those are on opposite faces. Therefore, the molecule is described as E. So certainly now you should be able to use the term Z and E in order to refer to the stereochemistry of any alkene group in a molecule. Much like we affixed the terms R and S at the beginning of molecular names where there were chiral centers that we could specify as R or S, we're going to affix E and Z terms at the beginning of names as well to specify the stereochemistry there. So let's go ahead, now that we've discussed the generalities of coming up with E and Z, to do another example problem of assigning molecules as E or Z. And then after we have that underway, we're going to go about incorporating this into the names of molecules. So let's go ahead with that. We'll take a look at this example problem, and as usual, I encourage you to hit the pause button and see if you can solve this yourself to determine whether you understand what we've just talked about with regard to assigning molecules as E or Z. So we'll go ahead and walk through the solution to this problem. And what we're going to do is we're going to take that carbon-carbon double bond, and much like I did in the first example problem, just to get my mind in the right place here, I'm going to draw a squiggly line through the double bond so that I am reminded to look at each of these two carbons of the alkene group individually and ask myself, relative to each of those two alkene carbons, which of the two groups directly bonded to that is higher ranking. So on the right hand side we have, for comparison, a carboxylic acid group and an alcohol group, CH2OH. So comparing those, we have to use the same method that we used for determining R and S stereochemistry, which is where we look at the first atom going away from that carbon of the alkene group. We see a carbon atom here. We look at the first atom coming up this way, and we see a carbon atom there. So those two carbons are indistinguishable. And so what we're going to do then is move down the chain one more spot by asking ourselves, what are the three atoms that that carbon down here, the carboxylic acid group, is directly bonded to? We'll do the same thing up here. I'm going to put those three atoms that are directly bonded there into our brackets. So the carbon atom on bottom here, remember that a carboxylic acid group, COH, is our fun abbreviation for a carbonyl group directly bonded to a hydroxy group. So the actual structure there that you need to recognize is that COH group really represents this, where the squiggly line is what connects to the rest of the molecule. So our carbon is actually a carbonyl group, which means that it is listed as being directly bonded to three oxygen atoms, because the one oxygen is double bonded there, so we count that one twice, and then the single bonded oxygen counts as the third slot there. We come up to our alcohol group, CH2OH. CH2OH listing the three atoms that are directly bonded to this carbon of the alcohol group in order from highest atomic number to lowest. we see that we have an oxygen atom that would have to be directly bonded to that carbon, as well as 2 hydrogens that have to be directly bonded to that carbon. So comparing what's in brackets for each of these 2 possibilities, we see that when we get to here, the middle, we have an H compared to an oxygen. Oxygen certainly has a higher atomic number, and therefore we can say that the COOH has a higher rank than CH2OH. We're going to come over to the other side, and we'll do the same thing for that carbon atom that has the red dot on it on the left. So we have to ask, bonded to that carbon, which of the 2 groups is higher ranking? The aldehyde group up top, and again, this is one of those abbreviations that you do have to remember, that CHO implies that you have a carbonyl group directly bonded to a hydrogen. That's our abbreviation that's standard for that. So there, we're comparing an aldehyde group to our tert-butyl group, and we look at the carbon atom here versus what would be directly bonded here would be a carbon atom. Remember, this has got to be the carbon atom of the aldehyde that's directly bonded to the alkene group. That carbon atom is directly bonded then to 2 oxygens, because we count the double bond twice, and a hydrogen. We come down here and do the same game for the tert-butyl group. We see that tert-butyl group is bonded to 3 carbon atoms, each of those 3 carbons of the methyl group. Now we compare what's in the brackets for these 2, looking for the first point of difference, the first atom we can use to differentiate. So that's going to be an oxygen versus a carbon. Oxygen has a higher atomic number, and therefore the aldehyde group is going to outrank the tert-butyl group there. So now, finally, to finish off, determining whether this is E or Z. If we're looking at the carbon on the right, we would have to go down to get to the higher ranking group. If we look at the carbon on the left, we have to go up to get to the higher ranking group, and therefore we can assign this molecule as having the E stereochemistry. So we describe this as E because the 2 higher ranking groups, that is the one that's bonded to the alkene carbon on the right and the one that's bonded to the alkene carbon on the left, go off in opposite directions, opposite faces of the molecule. And by the way, at this stage of the game, I would not expect you to be able to come up with a full IUPAC name for this particular molecule, because you see that it has about 4 different functional groups incorporated into it, and we definitely have not yet learned how to name alcohols, carboxylic acids, or aldehydes. So that's something that would come later on, much further down the road. For now, you should just be comfortable with assigning molecules such as this one as E or Z. On the other hand, if I give you a molecule that is a hydrocarbon, alkene, meaning it doesn't have any heteroatoms in it, or if I give you even a molecule that has a halogen atom incorporated into the alkene, you should be able to incorporate the EZ into the name of the molecule. So let's go through how to go about doing that via an example problem. Onward with this example problem. As usual, I advise you to work through on your own trying to come up with the IUPAC name for this molecule. And then to include the stereochemistry in the name, what we'll do is at the very beginning of the name for the molecule, we'll put the E or the Z into parentheses. We'll also be including the R or S notation at the beginning of the name in parentheses as well. So go ahead, give this a try, then hit play when you're ready to look at the answer to it. So looking at the solution for this problem, first things first, in coming up with the IUPAC name for this molecule, which is a review of our discussion of naming molecules of multiple alkene groups, we need to come up with the longest carbon chain that passes through both of the alkene groups here. So our longest carbon chain passing through both of the alkene groups is what I'm highlighting for you in yellow. And then to decide how to number that chain, we start at the end that is closer to an alkene group, because the alkene group takes priority over branches in deciding where to start numbering. So we'll start numbering from the end closer to the alkene group, which is going to put us starting right here, because that puts the alkene rolling in at carbon number 3. Whereas if we start from the top end there, our alkene group wouldn't appear until carbon number 4. So we number like so, giving us a total of 9 carbon atoms in our chain. We have 9 carbon atoms in the chain and 2 alkene groups. Therefore, the parent name of this molecule is nonadiene. So we'll go ahead and fill in nona for our 9 carbons, and then diene to indicate that there are 2 alkene groups. And remember that, as always, we need to specify where those alkene groups are located. These are located at carbon number 3 is one of the places the alkene group starts, because it's between 3 and 4. We also have another one starting at carbon 5, so therefore we call this 3, 5, nonadiene. An alternative for this is to call it nona 3,5 diene as an alternative to 3,5-nonadiene. All right, so onward from there. Now we need to go in and come up with names for the branches as our second order of business here. We have several branches to contend with here. So we have our methyl group here, our isopropyl group right here, or 1-methyl ethyl, and we have our chloro group right here. So we're going to go ahead and list those in alphabetical order here at the front of the name and indicate where they're located at along the chain. So alphabetizing this, chloro comes before isopropyl and methyl. So I'm going to put my chloro first. So I'm going to say it's 7-chloro dash, and then we indicate that the isopropyl group is at carbon 5, so 5-isopropyl dash 3,6 dimethyl dash 3,5-nonadiene. So that will take care of everything that we've highlighted here in yellow, blue, and red out of our structure. Now we're left with that business of identifying the stereochemistry that's going on here. So when we say stereochemistry, what we're referring to is the stereochemistry of any alkene group that we can specify as EZ, and we're also referring to any RS stereochemistry. So don't forget the RS information. All right, so taking a look at this and looking for our chiral centers, that is carbons that have 4 different groups bonded to them that we can recognize as RS. It's a good idea to look for your wedges and dashes here and ask if those wedges and dashes represent chiral centers. And here at carbon number 7, indeed, we have some wedges and dashes going on there to represent that chiral center. So we'll need to specify the chirality there at carbon number 7, and we will also need to look at the stereochemistry of our alkene group here and here. So we're going to take a look at those 3 locations that I've outlined in green there for the RS or EZ stereochemistry. So right here, since we have a chiral carbon, a carbon with 4 different groups bonded to it, we're going to specify this as R or S. The way that we do that, as a refresher, is we look at the atomic number of the atoms that are directly bonded to the chiral center, remembering that the hydrogen is omitted and the hydrogen would have to be a dash pointed away from you. Okay, so highest ranking group that's bonded there is, of course, our chlorine atom, so I'm going to put that as number 1. Second highest ranking group, if you go through and compare an ethyl group, which is headed over toward carbon 8, to the alkene group there headed toward carbon 6, we would find that the alkene group is going to put us with a higher rank, so we'll put that as number 2. Number 3 is going to be the ethyl group, so now we go from 1 to 2 to 3, starting at the bond leading to 1, passing through the bond leading to 2, ending at the bond that leads to 3. That takes us clockwise, and since the hydrogen is pointed away from us, we can therefore specify this as R. It is the correct-handed clock, the clock that runs toward the right. So we'll call that an R chiral center there at carbon number 7 of the chain. Now what I'm going to do is just go in and quickly erase here some of that scribble that was located in here, because we need to go in and specify here at carbon number 6 and 5 whether the alkene group is the E or the Z. So taking a look here at number 6, we need to ask ourselves which of those 2 groups is higher ranking. Is it going to be higher ranking to go up toward the chlorine and carbon, or down toward the methyl group? I'm definitely going to say that coming up toward the chlorine carbon bond is higher ranking. You could draw that out if you needed to, but that's going to be higher ranking going up to there. So I'm just going to put, getting kind of congested here, but I'm going to put some red highlight there to indicate that relative to carbon number 6, going up to that carbon chlorine bond is higher ranking than going down to the methyl group that's bonded there. We come over and we look at carbon 5, because remember carbon 5 would be on the opposite side of our squiggly line there. And we ask ourselves there at carbon number 5, which is higher ranking, having an isopropyl group there, or instead having an alkene group there. And what we would find is that our alkene group is going to end up being higher ranking if we systematically work through the ranks there. So I'm going to put a highlight on that to emphasize that is the higher ranking group. So now comparing the location of the carbon that's bonded to the chlorine to our alkene group there at carbon 3 and 4. That will indicate to us that one of those bonds is going up, the other one's coming down. Therefore, the carbon 5 to carbon 6 alkene would be assigned as E. So I'm going to mark that in as E. And then from there, we go onward to assigning the chirality, to assigning the stereochemistry at the carbon 3 to carbon 4 bond. So again, that between 5 and 6 was E. Okay, so looking at the carbon 3 to carbon 4 bond, we kind of draw a squiggly line through here to help us frame out what we're looking at. Then we look at carbon number 3 there, and we ask ourselves which is higher ranking of the two groups bonded there, ethyl group or methyl group. The ethyl group is going to be higher ranking, so I'm going to go ahead and put some red highlighting on that. Then we come over to carbon number 4 of our alkene, and we remember here that there's an unwritten hydrogen that's coming off right there. So we're comparing a hydrogen to carbon number 5 of the chain. Certainly carbon has a higher atomic number than hydrogen, and so therefore the winner is going to be up here that I've outlined in blue there. So now our two higher ranking groups, that is the highlighted group, ethyl group there, in pink on your right, and the blue carbon number 5, are both on the same face of the molecule relative to the carbon atoms that they're bonded to of the alkene. You'd have to go up to get to both of those. And so therefore we would describe this as being the Z configuration. All right, so now that we have assigned the stereochemistry at the RS chiral center and at these EZ stereocenters of our alkene group, now we need to plug this information into the name of this molecule. And the standard procedure here is that you list the EZ stereochemistry before the RS stereochemistry in the name. I'm not super picky about that, to be completely honest. On exams and things like that, I'm much more concerned that you're able to accurately assign these than that you're able to get them in exactly the right order here at the front end of the name. But just so you know, if you're ever in a situation where you have to decide, RS generally comes before EZ. So let's go ahead and do it that way to get things underway here. So we're going to specify the RS chirality at carbon number 7. So I'm going to call this 7R. And since that is the only RS location in the entire molecule, it would be okay to just list this as R. And much like what we did back when we were doing the assignment of RS and plugging it into names, we put it in parentheses. And then next up, we come over to the EZ locations. And for the E's and Z's, we do have to specify where those are located because we have two different ones. So we need to know which one is which. So at carbon number 3, we saw that it was Z, and so I'm putting 3Z. At carbon number 5, we saw that it was E, so I'm putting this in as 5E. And those numbers that we're assigning there, the 3 and the 5, should match the 3 and the 5 that we have down here, indicating where the alkene groups are. So with that, we've specified the location and name of the particular configuration that's going on here. So we put RS first in the name, and then the EZ designations second. So with that, hopefully now you are comfortable with assigning molecules as E or Z based on the configuration of the alkene group, and are comfortable incorporating that terminology into the IUPAC names for molecules.